morning, everyone. Thank you for coming to the class. For today, we will see another technique for simplifying a recurrence and finding the theta estimate of a recurrence. As you may remember, we started the concept of recursion last week. And today, again, we will continue this concept. We have seen substitution technique, which can be used to find the theta estimate of a given recurrence. Today, we want to see another technique, which is called recursion tree. Then we will solve two more problems of extracurricular number 2. As I explained before, we do not collect this extracurricular today. We will collect extracurricular number 2 on Friday. The solution of this extracurricular will be posted on Carmen by Monday. So I have also posted 3 practice problems, one for asymptotic behavior of function, another for for loop while loop analysis, and one more recurrence and recursion. These problems are very helpful because all of them come with solutions. When you go on Carmen on module, you can find them, solutions of problems and problems without solution. I strongly suggest you use these problems for practicing. You can get a very good idea how to approach the homework problem. And when you want to make yourself ready for the midterm exam and final exam, also these problems are very helpful. For some of you who were in my Foundation 1 class, you know that usually in my Foundation 1 class, also I use these problems, very helpful problems. The due date for homework number 2 passed. I will post the solution of homework number 2 soon on Carmen. And I have posted homework number 3. Homework number 3 is a little bit complicated, time consuming. Let's see that if extension for that homework is needed or not. I will take care about that soon. Okay, so questions, comments? Okay, perfect. So then first let's see about recursion tree. Then we will solve extracurricular problems over here. And then we will see some special recurrences. And at the end we will see one theorem, master theorem. First, recursion tree. Recursion tree is another technique for finding the asymptotic behavior of recurrence. Here we have one example, Tn equal to Tn over 3 plus T2n over 3 plus Cn. Okay, we want to show that asymptotically this recurrence is n-log. That's what we want to show. And when we start the concept of the quick sort, we will see that this recurrence is very helpful recurrence. How recursion tree can be? First, recursion tree is a rooted tree, and this rooted tree also is labeled. And I'm saying that it is labeled means that we have a label on each node. The number of branches for a recursion tree is same as the number of recursive calls. For example, here we have 2 recursive calls, Tn over 3, T2n over 3. Then there are 2 recursive calls. Therefore, every node has 2 children. If you had, for example, 3 recursive calls, then every node has 3 children. The number of nodes, the number of children of a parent can be identified by considering the number of recursive calls. And here, since there are 2 recursive calls, then every node has 2 children. How we can label each node? First, root is labeled by the cost. Here, cost of the given recurrence is Cn. Therefore, as you can see, root of this tree is labeled by Cn. There are 2 children for Cn because there are 2 recursive calls. Then how we can find the label or cost of children? When we want to find the cost of children, you just need to replace n of the parent with n over 3 and with 2n over 3. For example, here we have Cn. If you replace n with n over 3, you will get Cn over 3. And if you replace Cn by 2n over 3, you will get 2Cn over 3. One more time. The parent here has the cost Cn. When you want to find the cost of children, you will replace n of the parent with n over 3 and 2n over 3. If you replace n with n over 3, you will get Cn over 3. If you replace n with 2n over 3, you will get 2Cn over 3. Make sense? Questions? And we will continue. For example, for Cn over 3, again, there are two children. See? When you want to find cost, you just need to replace the n of the parent with n over 3. If you replace, because the parent here, parent here is Cn over 3. When you replace n with n over 3, you will get Cn over 3 squared. When you replace n with 2n over 3, you will get 2Cn over 3 squared. And same story for the second child of the root. Again, if you replace n with n over 3, you will get 2Cn over 3 squared. If you replace n with 2n over 3, you will get 2 squared Cn over 3 squared. And these costs can be identified by replacing n in the parent with n over 3 and 2n over 3. The same story we can continue. For example, here I didn't write it here, but okay. If we replace n with n over 3 here, we will get Cn over 3 cubed. 2Cn over 3 cubed. 2 squared Cn over 3 cubed. And continue. 2Cn over 3 cubed. Cost of these notes make sense for everyone? Questions? Comments? Don't be shy, Kazi. I will continue this procedure. The recursion tree can be found by using this procedure. As you can see, recursion tree is a rooted tree. Every parent has 2 children. Why every parent has 2 children? Because we have 2 recursive calls. And every node can be labeled by considering the n of the parent and replacing n of the parent with n over 3 and 2n over 3. Why n over 3 and 2n over 3? Because these are the input of the recursive calls. When you look at the recursive calls, you can see that you have Tn over 3, T2n over 3, then input of recursive call are n over 3, 2n over 3. That's the reason that you are replacing n with n over 3 and 2n. Recursion tree is a finite tree. It means that we do not have infinitely many nodes. Then the question which should be answered here is how many levels we have. It means how deep we can go down. So this tree that we have here on the slide is not very accurate. I will explain what is the more accurate form of this tree. And then I will explain why asymptotically we can assume this tree is accurate. If we do not consider the asymptotic case, this tree is not accurate. In other words, as you can see, this tree that we have here is a balanced tree. But in reality, the tree that we have here is not balanced. And we will explain that in what way we can say that this tree is not balanced. Then we will explain that here, in order to find the number of levels that we need to go down, then we will understand that why tree is not balanced. I think it is better to write it on a board. Okay, so the theory that we have here is a theory like this. Then you have Cn, then you have Cn over 3, 2Cn over 3, we have Cn over 3 squared, 2Cn over 3 squared, 2Cn over 3 squared, 2 squared Cn over 3 squared, and continue. Okay, that's what we have here. Okay, a little bit terminology of the concept of trees. We will see this terminology this semester a lot. As you know, these stuff are called level. People start counting levels from 0. Therefore, this is 0's level. This guy is first level. This guy is second level, and continue. Third level, you will go down. So, the interesting question here is, what is the maximum number of levels? You may remember from Foundation 1, if you don't remember, we will see this semester, the maximum number of levels is called height. Therefore, the interesting question for every tree, here, binary tree, is that what is the height of this tree? What's the maximum number of levels? In other words, how much deep we can go? That's the question that we need to answer. So, in order to answer this question, we can say that we will go deep until, because you see what's happening here for cost. Cost of this guy is Cn over 3. Cost of this guy is Cn over 3 squared. If you go one level deep, you have Cn over 3 cubed. One level deep, Cn over 3 to the 4. Then what's happening? Costs are getting smaller and smaller. Then you have Cn over 3 is smaller, Cn over 3 squared is smaller, Cn over 3 cubed is smaller, Cn over 3 to the 4 is smaller. Then here, what you are doing when you are going deeper and deeper, you are making costs smaller and smaller. Then the interesting question which should be answered is that how much we can make this cost small. This question is easy to answer. You will continue making this cost smaller and smaller until you reach to 1. Then costs must reach to 1. In other words, when we go down and down, we want to continue until we reach to 1. When I'm saying that reaching to 1 means that here, for example, my goal is to find k for which we have n over 3 to the q, n over 3 to the k is 1. Then here, when I'm saying that these costs should reach to 1, then eventually we want to reach to 1. It means that from this side, at least, from the left side, when you are dividing n by the powers of 3, you want to find the power for which n over 3 to the k is 1. Then my goal here is to find k. Find k such that n over 3 to the k is 1. When you reach to the case that n over 3 to the k is 1, because you have c, then on the bottom you have, suppose for example, n over 3 to the 4 is 1. Then here you have just c. But c times 1 is c. Now we can explain why this tree in reality is not balanced. So someone can say that, wait a moment, from this side it seems that you are considering the powers of 3. But from this side it seems you are considering power of 2/3. Because see 2/3 squared, one level deeper, 2/3 cubed Cn, 2/3 power 4 Cn. Then it seems that we have powers of 2 different numbers. More precisely, here you have powers of 1/3, here you have powers of 2/3. The same thing can be written here. It means that my goal is to find, say, k prime, such that 2/3 to the power of k prime times n equal 1. See, from one side, you are considering the powers of 1/3. From another side, you are considering the powers of 2/3. More precisely, we can say that if you consider left side, powers of 1/3 are being considered. When you consider right side, powers of 2/3 are considered. Then someone can say that this k prime and k. Or precisely, someone can say that the equation of this, the solution of this equation and solution of this equation are the same. We will see no. We will solve this equation and we will see that no, the solutions are not the same. Then let me, solution of these equations are easy, but like this here. Okay, so then if we solve the first one, you have n over 3 to the k equal 1. Then that's the equation, 3 to the k equal n. Therefore, k equal 2 log n base 3. For the second one, you have 2/3 over k prime times n equal 1. If you solve this, you have 3 over 2 over k prime equal n. And then k prime equal to log n, because 3 over 2 is 1/2, then you have log n 1/2. These two logarithms are not the same necessarily, because we have two logarithms with the different bases. Therefore, these two logarithms are not the same. This guy is log n 1/3, this guy is log n base 3. Which one is bigger? Log n base 1/3. Then if you want to be more precise, we can say that log n base 1/5 is bigger than log n base 3. Then more precisely, you can say that here k prime is bigger than k. K prime is bigger than k. Do you know what does it mean? It means from one side you will reach to the last level faster. More precisely, you can say that from left side you will reach to the last level faster. Let me come back to this. Then here we can say why. Because I have k prime, this is easy to see that k prime is bigger than k. When you say k prime is bigger than k, it means that you will reach to the level k. Say, for example, level k is here. Level k. At which, from here, you should stop. You will reach to C. But still, there are some nodes from another side, because you have k prime deeper. K prime is deeper than k. Then it means when you reach to the level k, you have no more nodes after level k on the left side, but you have more nodes after level k until you reach to level k prime. That's the reason that this tree is not balanced. It means that in reality, tree is like this. In one side, we stop on one side, we need to go deeper. Then this tree is not balanced. The balanced form that we have on the slide is not very accurate. Because in reality, we know that k and k prime are not the same. K prime is bigger. Any questions? Any comments? Any questions? Any questions? Everybody's following my logic? Makes sense what we are saying? That you have two levels here. One level that at which left side stops. What level at which right side stops? Yes. Yes, but I didn't say anything about worst case and bad case. Maybe worst case and good case. Then I just want to make sure everybody understand up to now. I just want to make sure everybody understands why this tree is not balanced. That's it. Makes sense? This makes sense? The one thing I want to make sure everybody understands is that right and left side do not reach to the last level in the same pace. We want to say from one side you will reach to the last level faster. Okay, so two questions here should be answered. Number one, if this tree is not balanced, why the tree that we have in this slide is balanced? because the theory that we have in the slide, it seems that right side and left side we reach to the last level in the same pace. Why? I made a mistake. Why I am allowed, or I was allowed when I was typing that slide, to have the same pace? Because if you look at the slide, you will see that both sides reach to the last level in the same pace. How can I say something like that? What do you think? Yes, please.
Because they have the same start point.
Yes, we have the same start at the same point, but how do you know that they will reach to the same level? More precisely, it seems that I am claiming K and K prime are the same. How it is possible to say that K and K prime are the same? K is log n base 3, K prime is log n base 1.5. How can I say that these are the same? Because it seems that something that we have in the slide is telling us K and K prime are the same. But why? Yes, Billy. What's your name? Levi, yes. Thank you. Excellent, Levi. Thank you. Asymptotically, they are the same. Because as we explained at the beginning of the semester, base of logarithm at infinity doesn't matter. Therefore, although these two logarithms are not the same, because one of them is log n base 3, and another is log n base 1.5. But if you consider these two logarithms at infinity, as Levi told us, if we consider asymptotic behavior of these two logarithms, we can say that they are the same. Therefore, log of n base 1.5 asymptotically is same as log of n base 3. Because at infinity, base of logarithm can be ignored. There's a very easy reason for this. Then here, log of n base 1.5 and log of n base 3 are the same. Then at infinity, although this theory in reality is not balanced, asymptotically this theory is balanced. The reason that here in the theory that we have in the slide, we have a balanced tree because we consider the asymptotic case. Means we assumed n is big enough, n is large enough. In that case, you can say that K and K prime are the same. Questions, comments? Any questions? Now let's find the upper lower bound for Tn. Okay, first let me explain on this then. How we can find Tn? When you want to find Tn, you have to find cost of each level. How cost of each level can be found? Cost of each level can be found by adding cost of nodes on that level. For example, in the zeros level, cost is Cn because you have just one. In the first level, cost is Cn over 3 plus 2 Cn over 3 against Cn. When you add costs of these nodes, you will get Cn. In the second level, again the same. If you add these costs, you will get Cn. Same story for this one. Then as long as all nodes are there, cost is Cn. But after K level, cost is not Cn. Why? Because there are some missing nodes. Therefore, we can say that after K level, cost is smaller than Cn. Because there are some missing nodes. When every node is there, then cost is Cn. When you pass K's level, cost gets smaller than Cn. How do I know that cost gets smaller than Cn? Because there are some missing nodes. If it was full, cost still would be Cn, as you can see in the slide. In the slide, since we assume every node, every level is full, then as you can see, I said cost of every node and cost of every level is Cn. But in reality, cost of every level is not Cn. Until K's level, cost is Cn. After K's level, since there are some missing nodes, cost is smaller than Cn. Then when you want to find Tn, you just need to add cost of levels. Then it can be written in this form, that Tn equal to sigma cost of levels. Then Tn is the sum of cost of levels. Means you have a bunch of levels, you will find cost of those levels by adding cost of nodes. Then after that, you will add cost of levels. The number of levels is finite, and the number of levels is same as height. Therefore, Tn here is equal to sum of cost of levels. So, but cost of levels, it seems that it's not known, because it seems that there are some missing nodes. Then what can be written? You can say that cost of these is less than the case that we have everything less than the case that no missing node and bigger than k levels, sum of k levels. Sum of k levels. If you consider k levels, then when you add just k levels, then cost for sure this sum is bigger. And if you assume no missing, this is not reality, but that one is bigger. Okay, if we consider k level, you have k times Cn. The cost of each level is Cn. Until k's level, you have no missing node. The cost of everything is Cn, then here I can say that k is Cn. This guy is bigger than Tn. And when you have no missing, means that the tree is full. When the tree is full, means that you have k prime level and every level has cost Cn. Then you can say you have Tn less than k prime Cn. Any questions? Any questions? Don't be shy, guys. This is not easy. Some may have seen something like this in foundation, or some may have not. Don't be shy if you find it hard. That's very, very understandable. I think you remember my funny joke, maybe funny joke. This is beyond the comprehension of this teacher, that somebody comes to this class and tolerates such an ugly face and doesn't understand anything and come back home. This is beyond my comprehension, seriously. And remember, something that I always say, no maker happen in the exam, because no graphic will be there. The same problem can be in the exam. And if you understand now, you'll be right in the exam. If you don't understand now in the exam, what you should do? Then in the exam is bad. Then if you find it hard, that's very understandable. This is a tough problem. And in most cases, when you understand, when you feel something is hard, you are not the only one. But do you know why other people do not ask any question? Maybe because they are not as brave as you. They'll be brave and ask. The worst thing that somebody can do is not asking question because feel that other people would say that this guy is not good. This is a tough problem. Then ask questions, comments, everybody is following how we got these inequalities. Then say I compared both sides and I considered two extreme cases. Extreme case here is that you have nothing after case level. Just consider k level. That's the way that I got this. How I got this? I consider every level is full. If you consider every level is full, it means that you have k prime level, every level is full. And in each level cost is Cn. Then I added k prime Cn, Cn, because see, Cn, how many Cn? K prime. Therefore, you can say that Tn can be bounded from below by k Cn, from above by k prime Cn. K and k prime are known. K is log of n base 3 times Cn. K prime is log of n 1.5 times cn. But as we explained, base of logarithms at infinity can be ignored. Then no base. Then see, bound on the left and bound on the right are the same, then what can be written? Tn belongs to the theta n log n. In the exam, in the homework, if you assume the asymptotic case, means if you assume k and k prime are the same, and if you assume the T is balanced, as we did in the slide, it's okay. Mathematically, that's a better answer. What's the difference between the answer that we have here, the solution that we have here, and the solution that we have in the slide? In the slide, the asymptotic case is assumed from the beginning. Therefore, T was assumed a balanced one. But here, we didn't assume asymptotic case at the beginning. When we reach to this inequality, asymptotic case has been considered. You got this? That was the problem. Any questions? Any comments? Any questions?
So we just cancel the 1.5.
Bases, yes, because when we consider that at infinite, bases can be cancelled. Then I cancel bases. We could cancel bases at the beginning. This is something that I did in the slide. In the slide from the beginning, I assumed that bases can be cancelled. Then asymptotically, T is balanced. Any questions? Any comments? Then you on Thursday, when you come also, I will find this integral by using cylindrical coordinate. By using cylindrical coordinate also we get polar rate. My understanding is for this question, spherical is easier. You will see on Thursday when we will find this integral in cylindrical coordinate. A spherical coordinate here is easier. When we want to use cylindrical coordinate, we need to use substitution technique from Calc 1, but if you integrate by using a spherical coordinate, if you use my bound or if you use Brandon bounds, for both actually you will see that you get some easy functions and you can integrate them very easily and find the answer polar rate. So, okay, any question?